Have you ever had it happen that you're learning this cool new thing in math and you're learning and learning and then you get to the end and there's just sort of nothing? There's no connections to the outside world, it's fully self-contained, and it kind of feels like it was just a big waste of time. I've had that happen with fairy fractions and matroids and Galois theory. Now, I don't know about the other two, but this video is about those missing connections in Galois theory. What we're going to do is we're going to talk about the main theorem of Galois theory, we'll explain how it's usually used, and then we'll fill in those missing connections. We'll give some examples, we'll do some problems, and sort of discuss how Galois theory was built to be applied. To introduce the fundamental theorem of Galois theory, we'll start with a basic question. Solve x to the fourth minus 2x squared plus 9 equals 0. This will be a stand-in for solving any polynomial, but this one is a little interesting. Generically, if we can solve irreducible polynomials, we can solve every polynomial, so we assume that they're only ever irreducible, as this one is. It has 4 roots, so let's call them R1, R2, R3, and R4. We'll say more about them later, but for now, we know that they all satisfy the polynomial equation they're roots of, so let's mark that down. Galois theory is about the interaction between two objects, the splitting field of the polynomial and its Galois group. We'll define both of these and see how they interact in our special case. We'll start with the splitting field of the polynomial. First, we explain what a field is. It sort of emulates the reals or the rationals. You can add, subtract, multiply numbers, and you can divide by anything that isn't 0. Some examples you're familiar with are the rational numbers and the complex numbers a plus bi, where a and b are real. I bring that second one up specifically because the complex numbers are what's called algebraically closed. Every polynomial has all its roots inside the complex numbers. We care about that property because of how we'll define a splitting field of a polynomial. Namely, we take its roots as complex numbers and the rational numbers and turn them into a field. So what this looks like is we collect all the rational numbers and each root as it lies on the complex plane. And then we take all sums, differences, products, and quotients too, and we collect them into a set and call it the splitting field. As an aside, some mathematicians won't like this definition because we're defining the field elements as specific complex numbers instead of an intrinsic construction, and they have a point, but hot take, without mentioning anything about the reals or complex numbers, or anything about ordering the numbers, there's no algebraic way to tell the difference between square root of 2 and negative square root of 2. Fight about this in the comments. So we just give ourselves the ability to talk about whichever root we want by specifying enough terms of its complex decimal expansion to uniquely describe it. So because of how open-ended our construction is, it definitely is a field. Adding or dividing or multiplying two expressions like this are still such an expression. The other half is the Galois group of the field, and for that, let us recall the equations that the roots satisfy. We write the Galois group of one field slash another, or over the other, like this, and we define it as the maps sigma from the top field to itself, so that, first, sigma is bijective, meaning that sigma hits everything and has an inverse. Second, sigma preserves addition. You add before and map over is the same as mapping each summand and then adding. In other words, we can pull the sum outside of sigma. Third, the same thing with multiplication. And fourth, the bottom field, here it's q, is left alone by sigma. And we'll rush through the proofs, but composing two of these gives a third. The permutation that leaves everything alone is one of them. Inverting a permutation is another permutation, and composition is associative. The do-nothing permutation leaves all permutations alone when composed with them, and composing a permutation with its inverse gives the do-nothing permutation in either order. So this set of permutations is what's called a group. But that's just terminology. What do we do with this set? Let's bring up the set of equations again. The first one says that R1 is a root of a polynomial. What if we apply one of these group elements to it? Remember that we can pull out addition and multiplication, and also that sigma leaves any rational number alone. So we're here. What does this equation mean? It means that if R1 is a root of the x to the fourth minus 2x squared plus 9 equation, then so is sigma of R1. But we know all the roots of that. They're just R1 through R4. So sigma R1 is 1 of R1 through R4. And similar calculations show that sigma of R2, sigma of R3, and sigma of R4, all of these are roots of the same polynomial. And none of them can be the same root because that would mean that their difference was 0, but then the original root difference was 0 too. So then all these sigmas just permute the roots, or just map them around to each other. But then once we've chosen where each of these roots themselves go, we can look at any other element of the field, and then what is sigma of this? We can just remember that sigma pulls through every operation, and we can say exactly where this conglomeration goes. So we learned that knowing where each root R1, R2, R3, and R4 go is enough to determine the element of the Galois group. Knowing where sigma takes the roots completely determines sigma as a whole. And not only that, but sigma preserves every polynomial equation that R1, R2, R3, and R4 satisfy, as long as the coefficients of the equation are rational. We call these equations redundancies. Beware that that isn't a standard phrase, I'm just using it because I think it captures the interconnectedness of the roots. In this case, we have the original 4 equations, but let's dig a little deeper. If we pull apart the equation, the coefficients actually give us more redundancies, probably ones you've heard of, and they're called Vieta's formulas. They relate the coefficients of the defining equation with the roots. The first one says that the sum of R1 through R4 is 0, since that's the second highest coefficient. The second one says that the sum of the roots 2 at a time is equal to -2, and we get the other 2 equations in the same way. These redundancies say that if we apply sigma to each equation, what we get is still true. But if you think about it, that doesn't really say much because these equations are symmetric in all the roots, so rearranging them in any order doesn't change that truth. So in the case where there aren't any other redundancies other than those that can be derived from Vieta's formulas, there isn't much restriction to the Galois group, and any permutation will work. That won't be the case here, but it's good to know for the future. Let's store these equations over here and find some more redundancies. If we plug in -R1, we get this here. We can pull the factors of -1 out, which cancel because they're even powers, and we end with a polynomial that happens to be 0. And hence, we prove that if x is a root, then so is -x. And then since we haven't yet labeled the roots, let us choose R1 to be the negative of R2, and R3 to be the negative of R4, and let's put those on our list. From R1's point of view, that still leaves some ambiguity between R3 and R4, so let's fix that. If we instead plug in 3 over R1, we get 3 over R1 to the 4th minus 2 times 3 over R1 squared plus 9. The algebra is to expand out the powers, put them over a common denominator, and factor out a 9 from the numerator. Then inside the factor is also 0, because R1 is a root, so the whole fraction is 0. So the original plug-in is also a root. That was 3 over R1. It should be clear that 3 over R1 can't be R1 or R2, because we could do some denominator clearing and find that R1 is quadratic, which it isn't. And so 3 over R1 must be one of R3 or R4. But the ambiguity we mentioned earlier means we can choose 3 over R1 to be R3, and 3 over R2 to be R4. We write these in the multiplicative form shown here, and add them to our list too. And finally, we combine the 4 equations to get these ones relating R1 and R4, and R2 and R3. We'll put those aside and declutter by eliminating the others. Now we use these redundancies to try and map out the entirety of the Galois group. Remember, a permutation of the roots is a Galois element if it leaves every equation alone. We pull out the ones involving R1 and decide where it goes. First, if it stays R1, then we know that wherever R2 goes is the negative of where R1 goes, so it is also fixed. And then the same thing for R3, wherever it goes must multiply with R1 to be 3, so it is also fixed. And then finally R4 must go to R4. So that wasn't very interesting. Let's do another one. Say R1 goes to R2 instead. Then again, wherever R2 goes, it's the negative of where R1 goes. So then R1 and R2 must just switch places. And then where R3 goes must multiply with R2 to give 3, so R3 goes to R4, and R4 goes to R3. Okay, so it kind of seems like there's only one Galois element for wherever R1 goes, since these redundancies force where R2, R3, and R4 go. We can just watch the autopilot for the others. If R1 goes to R3, then R2 goes to R4, which is its negative, and R3 goes to R1, which is 3 over it. and R4 goes to R2. And the final choice for R1 is R4, and R2 goes to R3, and R3 goes to R2, and R4 goes to R1. So instead of this ugly list, these diagrams help visualize better what's going on, what the 4 Galois elements are. We call swapping R1 and R2 and R3 and R4 sigma, and we call swapping R1 and R3 and R4 and R2 tau. And then the final element is just doing one after the other. R1 goes to R3, then to R4, etc. So we write it as sigma composed with tau. And now that we understand the splitting field in the Galois group, let's introduce the fundamental theorem of Galois theory that relates the two of them. It says, if we have a polynomial whose splitting field is k, then there is a map between subfields of k, that means fields inside k, and subgroups of the Galois group, that is, smaller groups inside the full Galois group. What is this pairing of groups and fields? If we have a smaller group H, we look at all the elements of k that everything in H leaves alone. Like the whole Galois group leaves the rationals alone, what do smaller subgroups leave alone? To explain this, we look at our example. What are the subgroups here? Well, there's always the trivial subgroup, including only the do-nothing map, so we'll put that at the bottom. And then there's always the full Galois group, including every element, so we'll put that at the top. Then we need E and at least one other element, but if we include 2 other elements, we need the third, so the remaining subgroups are just the identity and each other element in turn, with lines between subgroups that contain each other. So the fundamental theorem says that the set of fields between Q and the splitting field should look like this. Let's verify that. We'll start with the easier two. What does the whole group fix? Well, we know at least the rationals. We'll derive one final equation that will help us with these. We take the equation that R1 satisfies, and then R1 times R3 is 3, so squaring that we can replace the constant term with R1 squared times R3 squared. Then canceling a factor of R1 squared, and moving 2 to the other side, we get R1 squared plus R3 squared equals 2. And so, there's a brute force explanation here proving that there's nothing more than the rationals that are fixed by everything that I won't go over. And so the answer to the question is the rationals, and the other chart has started. The other easiest subgroup is what is fixed by just the identity, and that's even easier, literally everything by definition. We can therefore slot that in its place too, and now we get to the interesting ones. How about just E and sigma, where sigma switches R1 and R2? Taking inspiration from Vieta, one set of fixed elements are symmetric polynomials in R1 and R2. For example, R1 plus R2. But remembering our redundancies, that's useless because it equals 0. What about the other symmetric polynomial, R1 times R2? I'm going to pull some magic out of my hat and add 1 and square. You'll see why in a minute, but if we expand this out, we get this polynomial here. And then R2 is negative R1, so we can replace all copies of R2 and collapse. But then we can add and subtract 8, and voila! The first part is familiar. It's 0, so it goes away. And we're left with negative 8. Thus, R1 times R2 plus 1 is square root of negative 8. And dividing by 2, we get square root of negative 2 is fixed by E and sigma. So the fixed field of the subgroup with only sigma is the rational numbers along with square root of negative 2, as we determined with a bit of magic. The next subgroup is E and tau, tau switching R1 and R3. By the same idea, we look at symmetric polynomials in R1 and R3, and this time R1 plus R3 will work. Again, using a bit of magic, we square it and expand out. But we derived R1 squared plus R3 squared equaling 2, and we knew from the start that R1 times R3 was 3, so we plug those in and simplify to get R1 plus R3 squared equaling 8. Again, taking a root, we will find square root of 8 is fixed by tau, and dividing by 2, we find that the field fixed by tau is q adjoins square root of 2. We can slot that in here too. And then finally the element sigma times tau that swaps R1 and R4, we know the drill. This subgroup fixes symmetric polynomials in R1 and R4, and we again look at R1 plus R4. We square it, expand it out, and remember that R4 is negative R3, and group terms, plug in our redundancies, and simplify to get a square equals negative 4. Thus the square root of negative 4 is fixed by sigma times tau, and dividing by 2, we know that the square root of negative 1 is 2. and hence we have filled out our whole diagram, thereby demonstrating the fundamental theorem of Galois theory in this specific case. The proof of this is pretty difficult, so we won't be going over it, but the next 3 sections will be discussing applications of it. But we can see here its power. We remove the infinite nature of the fields, and we replace it with a finite analog that at the same time captures the entirety of the field structure and abstracts away any mention of the field into an object we can study on its own. And then just to show how Galois theory can help us solve equations, we take the 2 equations we found involving R1 and R3 and R1 and R4 and add them. Then we can pull 2's out everywhere and recombine. But R3 plus R4 equals 0. So we're here, and we finally divide by 2 to get this value of R1. And then because we have all these relations between R1 and the other roots, we know the values of R2 and R3, which is 3 over R1, and finally R4. So this is kind of a flash forward to the next section. We're able to solve equations like this by breaking down the Galois group, and we'll come up with a condition on the Galois group that solvable equations need to satisfy. Before we go any further, let's discuss some terminology I'm going to use. So we know the definition of the splitting field of a polynomial, but the fundamental theorem as it was written said if the field is a splitting field, as if being a splitting field is intrinsic and unrelated to any particular polynomial. In fact, that's true. We'll prove that if P is irreducible with coefficients in some field K, and L is the splitting field of P, then every polynomial with one root in L has every root in L, and hence L is the splitting field of all those polynomials too. That will prove that being a splitting field is only about the field itself and the field K below, nothing about any specific polynomial. So how does this go? Take any random element of L, which we know looks like a combination of the roots of P in any order you want, and suppose we have some Q with that as its root. We need to show that every root of Q is in the splitting field, which means that every root of Q can be written in terms of the roots of P. That should feel obvious, but why is it true? What we're going to do is look at x minus this random number, except instead we're going to apply every element of the Galois group to it and multiply them all out. If we expand this out, Vieta's formulas say that the coefficients are symmetric in all the roots. So if we take any one of the coefficients and apply any Galois element to it, all we're doing is rearranging the terms of the sum, so each coefficient remains fixed. Thus, by the fundamental theorem, since the coefficients are fixed by everything, they're all in the base field K. What does that mean? Well, we found a polynomial R that has coefficients in K that has our random number as a root. But the important thing about R is that we know all the other roots too. They're all Galois elements applied to the original, so they're all in the splitting field. And so if we take the GCD of R and the original polynomial Q, we know that the answer also has coefficients in K and has at least one root. But Q was irreducible, so the GCD must be Q itself, and every root of Q is a root of R, which is in the splitting field. And we're done. And so for special fields like this that are splitting fields over K of some polynomial, we call those Galois extensions of K. Notice how L being a Galois extension depends on K. We need L to be the splitting field of a polynomial whose coefficients are in K, and not every Galois extension of K is a Galois extension of every other field K prime. Keep that in mind. But let's explore that. Say F is a small field, K is a Galois extension of F, and L is a Galois extension of both K and F. Because they're Galois extensions, and hence splitting fields, there are associated Galois groups L over F, L over K, and K over F. How do these relate to each other? If we break apart the language, then Galois of L over K is the rearrangements of L that fix K. So they're rearrangements of L. But also, Galois of L over F are rearrangements of L too. And if something fixes all of K, then it certainly fixes all of F. So everything in Galois of L over K is inside Galois of L over F. So that's one big connection. If the top field is the same, then two Galois groups are in the same big group and might be contained in each other. But what about Galois of K over F? The idea is that there's a map called forget that takes Galois elements of the big group, rearrangements of L, and forgets how they act on everything except K. There's the technical requirement that all permutations of L send everything in K back to K, or else the forgetful element wouldn't necessarily need to be a permutation of K. But this is true because K is a Galois extension of F. And if we take anything in Galois of L over K that already fixes K, and forget everything about it except how it acts on K, that certainly gets mapped to the identity, the do-nothing. So Galois of L over K is contained in the kernel of this forgetful map, the kernel being the things that map to the identity. If you know group theory, that means that Galois of L over K is contained in a normal subgroup of Galois of L over F. If you don't, let's break it down. Take any element H in Galois of L over K, and any random n in Galois of L over F, and any random x in K. So we have three things, H, n, and x. Then since x is in K, and K is a splitting field, applying any Galois element to it, namely n inverse, leaves it in K. And so since H fixes everything in K, H applied to n inverse of x is n inverse of x. Apply n to both sides, and we see that n inverse of x equals x. So since x was random, n inverse fixes all of K. So if n is anything in the big group and h is in the subgroup Gal of L over K, the conjugate of h, which was n inverse, was also in the subgroup. This is another definition of what it means to be a normal subgroup. And the quotient is defined as what we get when we apply the forget map, and is a subgroup of Galois of K over F. We didn't show this, but it's actually equal to Galois of K over F. In other words, every rearrangement of K can be extended into a rearrangement of L. We can always go backwards from the forgetful map. Now we'll discuss the original usage of Galois theory to determine when a polynomial could be solved by radicals. We'll start by taking the radicals of 1. The solutions to x to the n equals 1 are called the roots of unity. Remembering that we're sitting in the complex plane, the nth roots of unity are exactly n equally spaced dots around the unit circle. The one with the smallest positive angle is called zeta n, and it turns out that all its powers are also solutions to this. If we plot them on the complex plane, here's what they look like. And now we'll ask a very leading question. If some field K contains all the nth roots of unity, and A is some element of K, is K adjoin the nth root of A always Galois? If we let T be this element, it satisfies T to the n equals A, or T to the n minus A equals 0. For this extension to be Galois, all roots of this must be in K adjoin the nth root of A. But the roots are exactly T itself, zeta times T, zeta squared times T, all powers of zeta times T. And all these are obviously in K adjoin T. So yes, in fact, K adjoin the nth root of A is the splitting field of this polynomial, and is hence Galois over K. Since that's the case, let's ask another question. What is the Galois group? Every Galois element multiplies the nth root of A by some power of zeta, so we can parametrize the whole group as elements sigma k labeled by which power of zeta they multiply it by. And if we look at how sigma k acts on any other root zeta to the u times the nth root of A, since zeta was already in the field k, we know sigma fixes it, so it just multiplies the nth root by zeta to the k. But that just means that sigma k just multiplies every root by the same power of zeta, so the k in sigma k is actually intrinsic. It didn't matter which root of A we took. And we can plot these in the same complex plane as the roots of unity, and draw, in this case, sigma 3. We know the Galois group acts by rotating these roots by a discrete set of angles, and hence there is a minimum rotation angle phi. Notice here I'm not saying that phi has to be exactly 1/nth of the whole rotation. It might be like we have drawn here, that the smallest polynomial that t is a root of isn't necessarily t to the n minus a equals 0. It could be something smaller, in which case not all nth roots of a are its Galois conjugates. But all Galois conjugates have to be some power of zeta times each other, and there has to be some minimal angle phi. And then we see that all other rotations are just multiples of phi. So the Galois group is just repeated applications, repeated powers, of this one generator rotation. When a group only contains powers of one element, we call it cyclic, so the Galois group of k adjoin the nth root of A over k is always cyclic. This one single step doesn't look so powerful, but it turns out to say exactly when you can solve a polynomial by taking roots. For example, look at this thing, composed of a fifth root, a square root, and a cube root. We're going to show what property the Galois group of the splitting field of this has to have. To build the splitting field, we start with Q. We add the third and fifth roots of unity to get the field K. It's easy to find the Galois group of K over Q. It turns out the first extension is cyclic of order 2, and the second is cyclic of order 4. But then we add the square root of 2 to K, and then the cube root of something in K adjoins square root of 2, and finally the fifth root of something in the previous field. By what we showed, each of these extensions is Galois and cyclic. Let me be clear, they're not necessarily all Galois over Q, but each consecutive pair of fields is a Galois extension. And so to create the splitting field of this original jumble of roots, we need to know its Galois conjugates. But it should be believable that they are all given by multiplying every root by some power of the appropriate root of unity. And so, if we let the intermediate field we constructed be f, we can build up the splitting field by adding in other roots that we skipped, root by root, where again, each consecutive extension is Galois and cyclic. To take stock of what we have a sequence of fields from Q to Kn, where the number we're concerned about is in the top field, as are all of its Galois conjugates. And additionally, this chain satisfies the property that each consecutive extension is Galois and generated by one element. I've been saying that we should stop at the splitting field of the root, but technically there's no reason that Kn should equal the splitting field. For example, we might not have needed to add all the cube roots or fifth roots that we did. If it's not, then we have to do one more move. We take the whole sequence and intersect every field with the splitting field L. After doing this, we have another sequence of fields, this time stopping at the actual splitting field, and we want to make sure that each consecutive extension is still Galois and cyclic. It turns out, yes, it is, but I'm not going to go over it. I'll provide two proofs, one on the field theoretic side, and one on the Galois group side, for you to peruse at your leisure. In any case, though, if p of x is solvable by radicals, we can create a sequence of fields from Q to its splitting field, where each consecutive extension is Galois and cyclic. This is the property that Galois discovered, but it's hard to prove anything with because we have to find the splitting field. Let's convert it into Galois theory language. If it's solvable by radicals, there is a sequence of subgroups of the full Galois group, Galois of Kn over Q, namely Galois of Kn over Ki, so that each is a normal subgroup in the previous, and the quotient is cyclic. In other words, there's an element g in each group, so that everything in the group is some power of g times something in the next smaller group. Abstracting away the sequence of groups, we find this description of the abstract groups. Ignoring the Galois of Kn over Q, we get the description of an abstract group that is given the name solvable, like a random group is called solvable if it has a sequence of subgroups with this property, unrelated to whether it happens to be a Galois group or not. And as we mentioned after the first chapter, the upside of Galois theory is we can study the groups on their own instead of remembering the field. For example, in the case where there are no extra redundancies beyond Vieta to kill off any Galois elements, every single permutation of the roots is acceptable, and this set of permutations is called the symmetric group on M letters, or SM. If we let that be the Galois group, we're looking for a sequence of subgroups as such. We'll prove that this is impossible when m is greater than or equal to 5, thereby proving that any such polynomial can't be solved by radicals. Okay, let's begin. Since Sm has every permutation moving 3 roots in a cycle you could ask for example, R1 to R2 to R4 back to R1, and nothing else moving, and the bottom group Gn obviously has none of them, there's some consecutive pair of groups, Gi-1 and Gi, where Gi-1 contains every 3 cycle that Sm does, and Gi is missing at least 1. Right, we're going down from Sm to nothing. Eventually you have to shed off at least 1 3 cycle, and let Gi be the first point at which you do so. Here's an example of what a 3 cycle might look like. You can see the 3 roots R1, R2, R4 permuting and everything else being left alone. We're going to show that Gi actually has no 3 cycles, and then explain why that is a contradiction for m at least 5. To prove the first part, the idea is if Gi had any, we could get from that one to any other by conjugating by something we know is in Gi-1, and using that gi is normal. So let's take two 3 cycles, 1 to 3 to 5 to 1, and 1 to 2 to 4 to 1. And given that the former is in gi, we want to show that the latter is too. We'll keep this handy diagram of the roots available to show where they go. So the first step is to copy the red, green, and blue roots into this diagram. We know this permutation is in gi minus 1 because gi minus 1 contains every 3 cycle. Let's draw the arrows on the diagram and follow them. And then the next step is to copy down our original element, which we know is in gi by assumption. Doing that on the diagram, we get this permutation. And then finally, we copy down the reverse, the inverse of our red and green permutation. Applying it on the diagram, we end with this. Writing down the permutation we've obtained, we get R1 to R5 to R2 to R1, which is in gi. And that's because gi is normal, and we conjugated something in gi, which always leaves it still in the subgroup, in gi. The diagram looks like this, and then taking the inverse reverses the arrows while still keeping the permutation in gi. And so notice what we did. We were able to replace the red root with the green root, still keeping within gi. That shows us the following. We can replace roots in the 3 cycle one by one to get from any 3 cycle we know to any 3 cycle we want. Doing the same thing with the R5 to R4 to R1 to R5 3 cycle, we can get to our goal of R1 to R2 to R4. So if gi has one 3 cycle, it has to contain them all in order to be a normal subgroup of gi minus 1. But it doesn't, so gi can't contain any 3 cycles. So we jump from gi minus 1 having all of them to gi having none of them. So now we use the fact that m is at least 5 to conjure up some very specific elements of gi minus 1 that will give us a contradiction. In particular, we use the R1 to R2 to R3 3 cycle and the R3 to R4 to R5 3 cycle. Because the quotient is cyclic, there's one generator g, so that everything in gi minus 1 equals some power of g times something in gi. That's just what being normal means and having a cyclic quotient means. So say that the first 3 cycle is equal to applying g m times, then something of gi. The second is the same as applying g n times and then something of gi. Then the inverse of 1 to 2 to 3 to 1 is 1 to 3 to 2 to 1, and is also the same as applying g negative n times and something of gi. And same for the other inverse. We can first see what happens when we apply these 4 3 cycles one after another, starting with 1 to 2 to 3, and then 3 to 4 to 5 cycles like this. Remove those arrows, then reverse 1 to 3 to 2, remove those arrows, and finally 3 to 5 to 4 cycles like this. This leaves the cycle 2 to 3 to 5, which is a 3 cycle. But remembering what we just said, this 3 cycle is the product of some powers of g and some elements of gi. And here's the fancy thing about normal subgroups. You're allowed to pull elements of them to the right through other group elements at the cost of changing which element of the normal subgroup you have. So here, we can pull A1, A2, A3, A4 all the way to the right, because they're all elements of the normal subgroup, and our only cost in doing so is to combine them into some other A question mark. That's just a fact about normal subgroups. Try to prove it if you aren't sure. And then the powers of g collapse, and we get that this 3 cycle was equal to A question mark all along, which is in gi, the group that can't have any 3 cycles. So this contradiction proves that there can't be any such reduction of Sm down to the identity by subgroups that are normal with cyclic quotient. And we care about this because any generic polynomial with Sm as its Galois group can't be solved with radicals, square roots, and cube roots. As a recap of what we just did, we discovered a criterion that Galois groups of solvable polynomials must satisfy. And we proved that the generic symmetric group with at least 5 roots doesn't satisfy this. We did it by finding where the Galois group first loses a 3 cycle, then proved that it can't have any 3 cycles or else it would have them all. Then we showed that if there is a drop-off like this, the quotient isn't cyclic. What actually happens is we drop from the full symmetric group down to the group generated by the 3 cycles, called the alternating group, and that quotient is cyclic. But then we have to drop from that down to the identity, and of course that's not a cyclic quotient. But that's just generic polynomials, and there's no reason to expect any particular polynomial to be generic. Anyway, remember we supposed that f contains the roots of unity. And we proved that if k is a radical extension of f, then it is Galois with Galois group being cyclic. I wrote it this weird way to be fully true and also to introduce Kummer theory. The main theorem copies down the first hypothesis, then the conclusion, and finally the second hypothesis. So it's kind of like a converse for the radical extension question, and in fact, if it's true, the criterion we needed to be true is also actually enough for it to be solvable by radicals. So we've sort of solved the problem of whether a polynomial can be solved by radicals completely. Its Galois group gives a full determination of the question. But how is this true? What we need to do is start with any cyclic Galois extension and produce an nth root of something in the bottom field that generates it. So let's take this number u here. It's the sum of x and sigma x over zeta n and sigma squared x over zeta n squared, all the way up to the n minus first composition of sigma of x over zeta to the n minus 1. Why this number? Well, let's take it and apply sigma. Sigma pulls through addition and division, and since zeta n is an f, sigma leaves it alone. Now we pull a trick. We multiply and divide by zeta n. Pulling out the factor of zeta, look at the rest. It's literally just u. So we learned that applying sigma to u gives zeta u. Let's bring that to the top. And so if u isn't 0, then this is the extension we want, because sigma of u to the n is u to the n, since the zeta n to the n becomes 1. But then sigma fixes u to the n, and so the whole Galois group fixes u to the n. And so the fundamental theorem tells us that u to the n is in fact in the lower field. But the only thing that fixes u itself is the identity. Everything else just multiplies it by some zeta power, so u must only be in k, nothing smaller. And hence k is f adjoin u, which is the nth root of something in f, like we wanted. There's just one hanging niblet left. What if we can't find an x where that combination is non-zero? Remember we said if u isn't 0, then yada yada yada. What if the u is always 0? Well, it turns out by what's known as independence of characters, that can't happen. And I'll leave this proof here for you to read, but otherwise we're fully done. We've completely determined when a polynomial can be solved with radicals, knowing only its Galois group. This trick we use to generate the u, of constructing a polynomial in such a way as to force the properties you want, is pretty powerful, and we'll use it later in the examples. So to wrap this section up, we'll prove that up to quadratics are solvable with radicals. To do so, we just need to give extensions and generators of the Galois groups to prove that they're cyclic. So starting with quadratics, we make a single jump to k1, the Galois group generated by sending a root x to p minus x, and obviously the roots are t and p minus t. One fun thing to do might be to look at what Kummer theory says about this quadratic case, just to check you understand how it works. Then to solve a cubic, we start by solving this quadratic to get what's called the discriminant. The t here is the product of the differences of the roots, that is, a minus b times b minus c times c minus a. This being quadratic, it certainly has z mod 2 Galois group, and the Galois group of the top field becomes a3. Then we can solve the original equation inside this discriminant field easier, because we have a cyclic Galois group now generated by this ugly quadratic in u. So this gives a proof that cubics are solvable, their roots in the end being u and these nasty quadratics in u. But you haven't seen anything yet. Let's solve the quartic. We start with the discriminant quadratic again, the roots being the same idea of the product of the 6 root differences. The Galois group here is z mod 2, which is the quotient s4 mod a4. Next, we solve this innocent-looking cubic, whose roots are ab plus cd, and the other 2 permutations of it, ac plus bd and ad plus bc. From where we are, this is solvable because the Galois group under the splitting field is v4, v4 being the elements swapping 2 pairs of roots. And we find this ugly transformation that generates the Galois group. Then we solve this deceptively simple quadratic to get v. V here ends up being a plus b or c plus d, and you can see that the sum of the roots is p by Vieta. This gives a Galois group of z mod 2 because we can swap a and b together with c and d. And then finally we solve w with this equation, which is another quadratic. Here's where we might have some trouble. If p equals 2v, the denominator could be 0, and we'd have to try a different pair of roots for v in the earlier step. But otherwise, we have one root a, which is w, another root b, which is v minus w, and then two extremely ugly roots c and d. This is all being provided so you can check, but the main point is that generic fields have Galois group Sn, and we provided a sequence of subgroups that break down S2 through S4 into cyclic quotients like we need. So that was our introduction to Galois theory, explaining the stuff that everyone does. But no one ever actually goes any further with it. It's used for solving polynomials. How do we actually do that? In the next video, we actually do some of these examples to show how Galois theory can be applied. See you there.